So today when we are working with starting to work with compound inequalities, we're going to actually be combining two simple inequalities, just like we talked about with compound words. Combine two words into one word, they become a compound word. Combine two simple inequalities into one inequality, they become a compound inequality. So let's fill in that definition. When two simple inequalities are combined into one statement, the result is called a compound inequality. So in the other lessons, we've been working with simple inequalities. Now we're going to put two of them together and work with them as a compound inequality. There are two types of compound inequalities. There's the type where we use the word and that is actually representing a intersection. So when we combine them and when we actually find the solution for a compound inequality that uses the word and in it, there's an intersection. In other words, whatever solutions we get, it has to meet both of the conditions. And so when we graph it, the graph is usually between 2 points. So we have to find the points that belong to both of them. We have to find their intersection. And so typically what happens on a graph of a compound inequality is it lands with that solution region lands between the two endpoints that belong to each simple inequality. The other one is called an OR. That is a union. Or in other words, we're putting the two of them together, working with them together, but it can be either one or the other. So we have kind of like a big pot to choose from. Our solution can come from that solution, or it can come from the other one's solution. When the two are working together, we actually have both options. It can come from just one or the other. It doesn't have to come from the intersection of them. It just has to come from the union of them. And that is usually outside the 2 points. Typically, when we graph an OR, you can pretty much count on that it's going to be outside the 2 points or opposite the 2 points is another way to put it. Okay? So let's start with the ones, remember there's two types, the and the or. Let's start with the and ones. Solving and compound inequalities, we do the same thing to all three regions to get x alone. So I'll show you what I mean. There's three regions in an and compound inequality. Number one is an example of an and situation. Here's how this one could actually be rewritten. And I just want you to do that over here. I want you to show that we can rewrite this as x plus 1 in the middle. We can read that one backwards, or in other words, we can kind of split this in two for a moment. We can say, here's one of our simple inequalities right there. -5 is less than x plus 1. That also could be written x plus 1 is less than. Remember, if we want the variable on the left side, what happens? We reverse the symbol, don't we? So we could make it is greater than -5. So that's one of our simple inequalities. The other simple inequality is the x plus 1 going the other direction. So the other one is, we say, and we have x plus 1 is less than 2. And notice we don't have to switch it around because the variable is already on the left. So there's our two simple inequalities that have been put together in the same statement. And when there's an and involved, that means the solution has to come from both of them. They both have to have that as a solution to be a solution for the whole thing. So here's how you have two ways to do this. You can separate it into the two simple inequalities that it is and solve each of them separate of each other. Or, as I suggested we're going to do, we're going to work with the 3 regions. So I'm going to get these out of there. And the 3 regions I'm talking about, here's a region right here, here's a region right here, and here's a region right here. Here's our 2 inequality symbols, right? We got 2 inequality symbols because we have 2 simple inequalities combined into 1. So we have 3 regions. So when we're solving this, whatever we do to get the variable alone, we have to do it to all 3 regions. So anybody have a suggestion what they think we could do to get x by itself in the middle? Cameron?
Subtract the sides with 1.
But we have to subtract 1 from
All 3.
all 3 regions, don't we? If we subtract 1 here to get x alone, we also have to subtract it from the other regions. So it's getting done in all 3 regions. So now we work down. What's -5? Take away a 1.
-6.
-6 is less than. We didn't do any multiplying or dividing, so we don't have to worry about reversing. X is now by itself in the middle and is less than 1. So this is saying, is x by itself now?
Yeah.
Yes, it's by itself in the middle, and that's the goal. So since x is by itself now this is really saying x is greater than -6. I'm going to read it from the middle out. X is greater than -6, and x is less than 1. So it's kind of like if we would have solved it over here where we have them separated, wouldn't we have subtracted 1 from both sides? And we would have ended up with x is greater than -6 and x is less than 1. So that's saying this is saying that same thing. So this is our solution. I want you to circle this. This is your solution. And now we're going to graph it. This is going to be a little bit different than graphing our simple inequalities was. When we did our simple inequalities, we only had 1 endpoint. And then we found the integer neighbors. Well, now we've got 2 endpoints, so we're not going to worry about the integer neighbors. We're just going to put both of those endpoints on. We're not going to worry about any neighbors. So we're going to put -6, 1. Is there -6 x has to be greater than -6. Is -6 included? In other words, do you think we should shade in the circle we're going to put at -6?
No.
No. We're just going to put our circle there and say -6 is not a solution because the equal to bar is not there for it. Then we go to the other side of the inequality and ask the same question. Is 1 included?
Yes. No.
No, because there's no equal to bar. It has to be less than 1, so 1's not included. And we have, so what we're looking for is we're looking for all the numbers that are greater than -6. Which direction do those go? To the left of -6 or to the right?
To the left. To the right.
Greater than, and then we got to look for the numbers that are less than 1. What direction do they go from 1?
Left.
They go left, so there's our intersection right there. Only the points, only the numbers between -6 and +1 are solutions for this compound inequality. Those are the only ones that will make the whole compound inequality true. Isaac?
Do we have to intersect like that? Or can we go to the left and one go to the right?
Not for an and one. No, unless, because we have, remember, it has to be the points that make both of them true. Okay, so let's check out a point. Can somebody tell me a number that does lie between -6 and 1?
-4.
0. Okay, 0's in here. It's probably about right here. 0. About there. Okay, let's check that out. If we put 0 in here, we would have 0 plus 1. What is 0 plus 1?
1.
1. Okay, so now we're going to see if this is a true statement or not. Is -5 less than 1?
Yes.
Okay, -5 is less than 1. Let's check out the other part now. Is 1 less than 2?
Yes.
Yes. So it makes the whole thing true. It's a point that satisfies both sides of it. So if we picked one that wasn't in that region, such as, how about 10? How about 10? 10's over here somewhere, right? It's not in our intersection part. Let's put a 10 in here. What's 10 plus 1?
11.
11. Is negative 5 less than 11?
Yes.
True. Is 11 less than 2?
No.
No, it works for a bit. Negative 5 is less than 11. True. But then it says, and 11 is less than 2. 11 is not less than 2, so that makes it false. So this is one of those situations where it has, again, our solutions typically will be between the 2 points. There should be right between them. Okay? Okay, let's try number 2. What do you think we should do first? Roach? Oh, you have a question.
Okay, so instead of just adding the opposite, subtracting when all three regions, could you just like combine like terms or something like that?
You can't combine like terms in this one unless they're within a region. Okay? So this 8 is its own region. It doesn't have anything to be put together with. 11's in its own region. It doesn't have anything. Okay? And the middle is its own region, and they're not like terms. Okay? So Trey?
Circle the 3 terms. Circle the 3 regions.
Yeah, so we got these 3 regions. We got 8, we got 3x minus 1, and we've got 11. What is it that we want to be by itself?
X.
Ariel? The x. So do you have a suggestion, Ariel? What do you think we should do first?
Add 1 to all the
Regions, right? Yeah, add 1 to all 3 regions. So 8 plus 1?
9.
9 is less than, what's going to be in the middle?
3x.
3x is less than or equal to 11 plus 1? 12. So what do you suppose we should do next?
Divide by 3.
Divide by 3, because it's not just a 1x in the middle, it's a 3x. So 9 is going to get divided by 3. Do we divide by a negative?
No.
No, so we don't switch the sign. 3x is going to get divided by 3. Is less than or equal to 12 is going to get divided by 3. So all 3 regions now get divided by 3. And what's 9 divided by 3? 3 is less than
X.
x. These cancel out. Is less than or equal to
4.
4. Okay, this is our solution, isn't it? This says x has to be between 3 and 4. Is 3 included?
2. No.
No, there's no equal to bar on that side. Is 4 included?
Yes.
Yes, there's an equal to bar on that side. So when we're graphing it, we say, okay, put a 3 on the number line and a 4. Don't have to worry about integer neighbors, remember, in these compound inequalities. We said 3 is not included, so open circle. 4 is included, so we're going to shade that one in. Make sure that you and I can tell. And where should we shade otherwise?
Let's hear what's in the left.
It says, let's remember how we can read this inside out. X has to be greater than 3 and less than 4.
Or equal to.
Or equal to. We already took care of the equal to part. So x has to be greater than 3. That goes this way. And less than 4. That goes this way. So it would be all these numbers in between. So we have our algebraic solution, and we have the graph that shows which numbers from the number line actually would make that inequality true. Any other questions on the and ones? We're going to do the or next. Okay, then let's go to the back side and try some ors. When you have an or compound inequality, you will see the word or written. you will see the word or written. And that, you cannot put them together like we just had in the and ones. You can't put something in the middle and the other ones on the ends. We can't make three regions. We have to solve each of them separately. We have to solve each of them separately. And then graph their solutions on the graph. Each of them, we're going to put their solutions together on the graph, but we have to solve each of them separate and use the word or in between them, just like how it starts out as. So, we have two simple inequalities here. We have 2 plus x is less than 12, or x minus 5 is greater than or equal to 9. We're going to solve them together in the sense that they're gonna have a solution with the word or in between them, and then we're gonna have one number line. It's still a compound inequality, but these two simple inequalities are not now combined into one statement. So we're gonna have to solve each of them independent of the other. So what are we gonna do in the first one? 2 plus x is less than 12. What should we do?
Subtract 2.
Subtract 2. And now x is alone is less than 10. Bring down the word or. What are we going to do to solve the other one? X minus 5 is greater than or equal to 9.
Add 5.
Add 5 to both sides. And what do we end up with? X is by itself is greater than or equal to 14. So we have a solution, an algebraic solution, that says x can be from either of these regions. It doesn't matter which one because there's an or in there. Clean your room or do the dishes. Chances are you're going to pick one or the other and not do them both, aren't you? So you get to pick a solution from one region or the other. So when we show that on the number line, we show the union of them. So we put the 10 and the 14. And we got to put them in their location where they actually are. 10 comes before 14 on the number line. Is 10 included?
No.
No. So we have an open circle. What numbers are less than 10? To the left or to the right? To the left. So we shade those. We say, those can be solutions. Or greater than or equal to 14 can be solutions. So is 14 included?
Yes.
It's included because of the equal to bar. And the number's greater than 14, so to the right. So you get to pick, if you were going to give a solution, if somebody said, what's one of the solutions for this? You could pick them from either region. It could be the numbers that are less than 10, or the numbers starting at 14 and getting larger. Any questions on that one? Okay, let's try this next one. So again, we have two separate, simple inequalities that together are going to have a solution. What are we going to do with this first one?
Divide by 7.
Divide by 7. Okay. And you know what? If you try to do both of them at the same time, here's what's going to happen. You're going to have your brain's going to carry over and say, okay, I got to divide by 7 in the next one too. But we don't. That isn't what we want to do in the other one. So we want to stay with the one you're doing. Is greater than or equal. Did we divide by a negative?
No.
No. 21 divided by 7?
3.
3. Bring down the word or. And in the other one,
Divide by 2.
divide by 2. What's our solution for that one?
X is less than or equal to 1.
Did we divide by a negative?
No.
No, so we don't have to reverse, and it's -1. Okay, here's our algebraic solution. Go ahead and try and graph that. Will you look up at mine very quickly and tell me whether I should go on or not?
No.
Why not? What's the problem?
You have negative 1 and positive 3.
Yeah, this isn't their location on the number line, is it? -1. And it's really easy to do this though, because 3 was first and -1 was there, so you just come down here, you put it on the number line, and you're like, presto. You have to stop and think and say, hey, wait a minute, -1 should be to the left of positive 3 on the number line. And then you're going to have to, as you're doing it, so you're going to look at should 3 be included? Yes? Okay. And I should shade to the right of those. Should -1 be included?
Yes.
Yes, and I should shade to the left of those. So be really careful. Treat each of them separate. Make sure you don't just automatically bring those numbers down and put them on the number line and say, okay, you go here, you go there, and not pay any attention to if they're in a good location or not. Okay, anybody have questions about that one? Did you get it to work out? Your graph? Okay, one more then. Here we are, we have 3x minus 2 is less than 7, or we have x minus 8 is greater than -1. So, what's going to be our first move in this 3x minus 2? Add 2. And now we have 3x is less than 9. It's our next move. Divide by 3. And what's our solution to that part?
X is less than 3.
X is less than, we didn't divide by a negative, right? Okay. What do we bring down next?
Or.
The or. We bring down the word or. Then we move back up there and say, okay, now I'm going to solve the other one. What's the other one? What's our move?
Add 8.
Add 8. Okay, what's our solution?
X is greater than 7.
Yeah, x is already by itself, and what? -1 plus 8 is what? 7? Okay. Okay, well, we don't need all that space to solve it, so we're just going to bring it down here and say, okay, there's the other part of the solution. And then we will graph it. So, who lives on the left? 3 or 7?
3.
3. Is 3 included?
No.
Are the numbers to the left of 3 included or to the right?
Left.
To the left. Okay. How about 7? Is it included?
No.
No. And what numbers are?
To the right.
To the right of it. Okay. So again, we get to pick a number from either region as a solution. And it's really important that we understand that when the word or is there, it doesn't have to do both. It only has to satisfy one of them. So if I picked the number 10, if I said, okay, 10, and I put it in here, is 10 less than 3? No, that's false. But it says or. So I get to toss that out and say, okay, well, I got another choice here. Is 10 greater than 7?
Yes.
Yes. So as long as it makes one or the other true, it's cool. Let's pick a number that's between 3 and 7.
4.
I like 5. It's right smack dab in the middle. Okay, is 5 less than 3?
Yeah. No.
No. Well, doesn't have to be. I got another choice. Is 5 greater than 7?
Yes. No.
No. That's why it's not in the shaded region then, isn't it? Because it doesn't satisfy either of them. Then there's no third choice. Okay, let's get out your loose leaf.